So I'm Andrei Stoian. I'm a machine learning director here at Zama, where I lead the machine learning team, which builds ConcreteML. ConcreteML the first version was released, I think, about 2 years ago. And since then, it has come quite a long way. The first versions were compiling some small neural networks. And the main challenge was fitting in with FHE constraints. So we explored many ways to make neural networks work, but also we added an array of other models. And today we're targeting large language models, which basically has become the mainstay of AI today. So my talk will be about 30 minutes long, and we can take questions at the end. But I'll first start with some, let's say, ideas about why one would use a ConcreteML. So why should we work with encrypted data for machine learning? So many people and many companies, initially when they develop a product, they don't necessarily think about protecting data, about privacy. But companies do have confidential data that they care about. So that's starting with that, the need for confidentiality becomes quite obvious. Everyone wants to protect their own data, not only companies, but individuals as well. So as a developer, we need to think about what the services that we develop, for example, with machine learning, what these services have as risks, what risks they have with respect to data leaking out, whether it's a company's data or the data of individuals that are processed by a company. So when working with private or confidential data, when doing analysis on this data, or predicting or training on users' private data, which contains personally identifiable information, one should consider using the FHE to secure this data. Another factor would be working with regulated data subject to data residency. So when data is transferred to a different country, which can be on a different continent, different regulations may apply. So using FHE will definitely go a long way to ensure that data stays secure and that the company stays compliant with respect to regulation. As a developer also, and this is actually one of the things that I was quite let's say interested in, is that as a developer you care about the privacy of the data that you handle. So for example, when you're building an application that manages user data, you'd like to handle this user data that is private in the same way that you would handle your own personal data. So if you want to apply this level of security for everyone, a good idea would be to use encryption. Finally, if in machine learning, when you develop machine learning models, sometimes you might not want to share them. So instead of sharing them, you can deploy them in a secure environment, but you can also have them process private data of your users. So you're both protecting the model IP and also the user's sensitive data. So let's look at some use cases. The most maybe intuitive one is private inference, when your data is processed by a cloud service and you would like to keep it secret. So you can get this privacy respected by using FHE and having the server process your encrypted data. Another one would be a data marketplace. In this sense, you're not sending your data to some specific service, but you're encrypting your data, and you can and applications will make requests to use your data. So a very simple example would be online advertising. Currently, browsers will track your actions. They will store this information in cookies, which are shared with advertisers. And this information that is tracked can, well, you don't have much control over it, and it can be quite personal. It can be identified based on this information. So a different way would be you can adjust what kind of information you want to share, and you can ensure that only what you want to share is used by advertisers by using FHE. So you're trusting the encryption to basically give access control to your data. So in that way, the data that you produce, and maybe this is some app on your phone that tracks where you run, some app tracks some, let's say your smartwatch tracks some health indicators. This data you can put it in some storage, and you can ensure that only approved applications have access to it. Another use case would be private training. So let's say a company that has confidential information would want to train, for example, a large language model to give answers on based on the knowledge that this company has accumulated. Obviously, the company doesn't want to share the data with the service that provides training of this large language model. But on the other hand, training such a model is very complex. You need know-how and you need hardware to do that. So you can train using FHE these kind of large language models on data that stays encrypted. And finally, AI agents kind of mix the data marketplace and private training. So you can imagine that you can train some large language model to write emails instead. So to give you some suggestions about an email that you're drafting, and you can give that suggestion based on data that you accumulate and that is personal. So you can basically speed up many processes in a personalized manner while still preserving the privacy of the data. Okay, so let's look at how we can do this technically. FHE at the low level relies on some very basic operations. We have addition, repeated addition, which means multiplication by a constant. And with TFHE, you have lookup tables that are implemented with programmable bootstrapping. So this operation reduces noise and also applies a function on the data. So this is something I guess many people already know. What I want to insist upon is that, well, knowing the operations is not enough. What the big issue is that because FHE relies on noise, there needs to be a very careful management of the noise levels in the different ciphertexts that on which these operations run. So this is a very hard problem, and I think in many research papers we get sets of crypto parameters that are more or less explained, and this is actually quite a daunting task to find these crypto parameters for when building a new application using FHE. So at Zama, the idea to get FHE to everyone, to get to every developer, to make it accessible, was to build a compiler. So we want to encapsulate all the complexity of finding parameters and writing code that maps to these low-level operations. So we built a compiler in Python, which is a language that is quite common in machine learning, and with the idea that a developer should not need to know cryptography to use FHE. So some of the cryptographers there might be disappointed that that we don't require users to know cryptography. Obviously, many people love cryptography. But developers that work with machine learning or other applications like blockchain, well, it's going to be hard to get them to learn cryptography, to tune crypto parameters. So we want to give them the best tools possible to do that, so they can focus on the problems that they know how to solve. So if you look at the code example using the FHE compiler, the concrete Python compiler is quite simple. We write a function in Python that performs some computation. We describe the status of the inputs, whether they're encrypted or not, and we compile the function on some in that step we give the compiler some values that show that the kind of values that this program will work on. As you can see here, this compiler supports working with integers, which is also related to the way the FHE scheme works at the low level. So we can also use floating point values in the code that we run, because as we mentioned earlier, we can build lookup tables which implement functions on integers. So we can have more complex programs that not only do additions, but also implement univariate functions on these integers. So when we write a program, what happens is that it will be translated into the structure that you see here on the right, which is a graph of operations, where we work with integers and we describe the floating point operations that are performed on these integers. And then in the second step, the floating point operations will be mapped to lookup tables that will be computed in FHE using the programmable bootstrapping mechanism. So we can take this program on the left, which is quite high level. We translate it into this graph structure that contains only TFHE compatible operations. And then when the crypto parameter magic happens, we use something called the optimizer to find crypto parameters by analyzing this graph and finding the optimal crypto parameters that respect the security level that is required by the developer, and also we optimize the computation cost. So we find the best crypto parameters that ensure the security level for this program that we expressed here in Python. Okay, so once we have that, we can think about more complex programs. And as we saw with the small example, we basically alternate between univariate functions and linear operations, which are sums of encrypted values. So then we can think of something like this big graph that has layers of univariate functions, followed by linear operations, followed by other univariate functions. And because these functions are implemented with the PBS, they reduce the noise in the ciphertext, so we can go on actually forever. We can also, let's say, at some point store the results that are processed here in this graph. We store them, then we process them later. We combine them with some newly generated ciphertexts, because the PBS keeps the noise level to what we require to continue working on this ciphertext forever. So the computation paradigm that we use in ConcreteML is that we use the optimizer to ensure that the sums, which are what we call leveled operations, are always exact. So we tune the, again, not a cryptographer, so I don't really remember the exact term, but we tune the crypto system parameters for these sums in a way that they are always exact. We allow the number of bits to grow to what we need. Obviously, with limitations, I think we're limited to something like 50 bits. Next, the univariate functions will be converted to PBS. So that will allow us to reduce noise. And finally, because when we will implement machine learning, we will be working with floating point operations. So we need to map those to integers. So not only do we need to map the univariate functions to table lookups, but we also need to apply quantization to ensure that these sums here, the linear parts, are correct when we're working with integers. So let's look at the graph for a machine learning computation. Logistic regression training is shown here. So we start with some data. We start with some initialized parameters, the weights and the bias. And we have the labels here, the Y variable. So this graph shows the operations that we apply on these encrypted values. Here, everything is encrypted, the data and the weights. This graph shows the operations that we apply in order to run one batch of data through the training algorithm. So some operations are univariate, like this sigmoid here. Some of them are linear operations. So we're doing additions, subtractions, sums. Some of them combine both linear and non-linear operations, like the multiplications of encrypted values. So to map that, when we work with machine learning, all this must be performed on floating point values. So to map that to integers, we use quantization, which basically means we will represent real values with integers through a fine map. We have these two parameters, the scale and the 0 point. And this basically maps the real axis to a segment on the real axis to a range of integers. So then we write the equations for the linear parts of the models using quantization. And what we want to end up with is some expression of the linear operations in the model that only use integers and lookup tables. So we take this equation here. So here we're performing a dot product, which is the most basic operation in a neural network, between weights and inputs. The weights can be encrypted or not. The inputs are always encrypted. It could be the training data or the inference data. So we rewrite the initial dot product between weights and inputs using the quantization equations. And then we can rewrite this equation to separate the integer parts from the floating point parts. So what you have here in the right box is the integer part that only uses the Q values and the Z values, which are integers. And on the left, you have this scaling factor, which is a floating point value. And this 0 point here, Z3, is an integer. So we split the equation in two, and then we will map this to lookup tables. So the operation on integers will be performed using the leveled linear operations. and the one on the left, which is the multiplication of the floating point value. This will be translated into a lookup table. So we have the linear part, and then we have the lookup table part, the scaling. And what's actually cool with the lookup tables is that any other univariate operation that works on this the result of this dot product, which is the activation of the neuron. Any activation function or batch normalization, which is quite common in neural networks, and the next quantization step can actually be fused in the same lookup table as the initial scaling. So then we get back to the graph of sums followed by functions, followed by sums, followed by functions, and so on and so forth. So everything that is in float will be fused. All these operations will become a single lookup table, which is also good for performance because we want to keep the number of PBS to a minimum. And then we feed the result of this lookup table to the next layer of linear operations and so on and so forth. So then we can implement basically any neural network, even very deep ones or large language models, for example. This can have hundreds of layers because the noise is reduced at each time. So we don't use polynomial approximations. Some other FHE schemes do that, but we don't. If we work on integers and we use quantization, all of the activation functions will be fused with the quantization and will become a single lookup table. Okay, so knowing how to do quantization and having a tool that allows developers to write programs that compile to FHE, well, we can actually build something even more high level. So that's why we built ConcreteML, which hides away all of this complexity. So ConcreteML exposes machine learning models that work directly on data without requiring the developer to provide implementations for the algorithms that power these models. So you don't have to know much about quantization. You don't have to write the computation code that implements these machine learning models. You can use them through ConcreteML. So you can apply them directly to your data that is floating point. You get results in floating point, and you have a whole array of tools to debug your models, to make them faster, and to analyze their performance. So again, you don't need to know cryptography, and you don't need to know the intricacies of quantization. You don't need to know how the machine learning model is implemented at the low level. So out of the box, you can already be very productive with ConcreteML. And we implement many types of models, classical ones such as linear models, tree-based models like decision trees, and boosted classifier, XGBoost, for example. We implement neural networks, which can be of varying size, small ones like MLPs, but you can implement big ones such as ResNet as well. We have a data frame API that handles some of the pre-processing of the data. When you encrypt your data, you want to track, let's say, what kind of pre-processing was done, such some quantization. For example, what the data types of the original data are, because you're mapping everything to integers in FHE. So with the data frame, you can track that, but you can also join data frames, which represent basically data tables. You can join them to find common rows between two tables. And finally, large language models For this, we implement inference, and very soon we'll release a feature for fine-tuning large language models on encrypted data. So let's look again at what the computation paradigm for all these models is. For the data frame, we're basically storing data, we're mapping data types that exist in the non-encrypted domain, such as strings and floating point values to integer values, which can be encrypted. So this data frame tracks that, and then it implements the join operations. So we have few leveled operations and a bunch of PBS operations. And here the data needs to be consistent at any point in time. So we use exact PBS computation. With PBS, we can adjust the crypto parameters to have full correctness, or we can allow some noise in the result of the PBS when that is acceptable. So for example, for linear models, we don't use PBS at all, but we have many level operations. So we built the optimizer to produce optimal crypto system parameters for this case. Tree-based models. In tree-based models, we do some comparisons and also some multiplications with clear values, some additions of ciphertexts. So for the comparisons, we use the exact PBS. It's important for tree-based models to get accuracy, that this comparison is exact. There's no noise in it. But there are some optimizations to make it faster, because comparing values to a threshold can be done by using only a few bits of the value. So we can do that with something called the round PBS. For neural networks, we have many leveled operations. So the matrices of weights can be quite big. So the bigger the model, actually, the more it is tolerant to noise. So then for neural networks, we use approximate PBS. We allow some errors in the result of the PBS. Again, the PBS implements the activation functions and quantization. We allow some noise, which improves the performance on such models. And finally, for large language models, we have a different computation paradigm implemented in ConcretML. We could compile the whole large language model to use FHE, to be fully in FHE, but the performance currently is too low. So we have a different computation paradigm. For LLMs, we suppose that the client and the server, or some computer to which we outsource computation, communicate, and they have a protocol in place. So the client will send just requests for computation on some parts of the language model, and then we'll orchestrate basically the computation between different worker nodes. The client will perform some operations, for example, activations on the client side. So then we outsource the computation and the memory requirements, because large language models require hundreds of gigabytes of RAM, which is very difficult to have as a developer. Okay, so let's see some examples. A simple one, image filtering. Well, to cryptographers, I guess maybe this is quite obvious, but many people discover FHEs through this example. What it does is just applies a simple filter to an image. And what we show here is that when we encrypt the image, it looks like noise. So this is obviously what one would expect if one is a cryptographer who knows how cryptography works. But so yeah, this is the kind of people. This is the kind of thing that people are quite fascinated about, because they see this noise image and then they see a second noise image, and then suddenly we decrypt this and something different pops out. So this is how many people get their minds around FHE. What I want to show is how easy it is to build this using ConcreteML. So to build this, you can use PyTorch. You give it an image. You can use PyTorch functions that permute the channels of the image to have it in the right format. And then you apply a convolution using the PyTorch API. You have a convolution kernel, so you can do many types of filters. And then you take the image and you put it back into what the web page, the application expects in order to display it. So you take this function and you compile it, and then that's it. And you get an image filtering application. So let's look at some more complex ones. For sentiment analysis, in this use case, you want to take a short text and you want to know whether it has a positive, negative, or neutral sentiment. So what you do is you extract some features on the client side. Basically, this gives you a big vector of floating point values. And on the server side, you run a classifier. And in this case, we built a tree-based classifier, and it gives you returns just the sentiment, which is a single value. So to build this with the XGBoost classifier, and what I want to showcase here is that with ConcreteML, you can basically work with these classifiers as you would do with the classifiers from scikit-learn that don't work on encrypted data. So you can tune hyperparameters of the classifier, for example, the depth of the tree-based model or the number of trees in the tree ensemble model. And you can iterate on this to find the best trade-off between the accuracy and the time it takes to execute this model with FHE. Once you have found the best model, you compile it, and then you can deploy it. We have an API to deploy these models, so you can build client-server applications with them. LLM inference. Not really showing many of the details here. So the idea, as I said, is that from a single user terminal, which is the client side, we will make requests to many worker nodes that do the FHE processing. And here we're trading off the execution, the hardware requirements on the client side with the number of worker nodes. So if you want to have a very light client, you'll be distributing your computations on several worker nodes, which load parts of the model, and basically the user device will orchestrate combining the intermediate results that are returned by these worker nodes in order to keep the private data on the device and only send encrypted data and do minimal computation on the client device. So one use case is, for example, fine-tuning LLMs. Here we're asking the LLM what is FHE, and this is the output from a model that we fine-tuned. This is some internal work where we fine-tune the model that did not know what FHE was, and then we ask it, once it's fine-tuned, we ask it what is FHE. And finally, still on fine-tuning, we're working on, so this is not yet released, but we're working on fine-tuning image generation models. These are quite popular. So you take a picture of yourself and then you send it to a cloud service that will fine-tune an LLM that generates images. So your personal pictures, well, these are kind of private. You don't want to send them and have them stored by some website that you don't know. And also, when you fine-tune an LLM, the results of this fine-tuning basically distill the information in the data, the initial data that you had. So the weights that are fine-tuned are also quite sensitive. So you want to keep them private. So with FHE, you can keep both the data private and the fine-tuned weights, but still apply the big LLM model on this data, and keep it protected. So here you're sending encrypted data, and once the model was fine-tuned, you send it a new request based on your image and the style of photo that you want to apply to your image, and it will generate this kind of photorealistic portraits in the style that you chose. So here we're outsourcing the computation power, because if you want to do this locally, you need a pretty big machine with a very expensive GPU, and you need know-how about fine-tuning models, installing all the software, and having the data science skills to do this fine-tuning. So okay. That ends my presentation, and thank you very much for your attention. We just before we go to questions, just want to point out that all of our code is open source, both for ConcreteML and the Concrete compiler, the optimizer, which finds crypto parameters. So the whole stack is open source, and you can build with it. You can take inspiration from the code, and you can, if you want, contribute to new features and learn many new things. And thank you very much for your attention, and let's go to questions.